Assalamu alaikum and hi. I'm Dr. Sidi from Faculty of Computer Science and Information Technology, University Putra, Malaysia. Today I would like to present a paper entitled The Skyline Operator Algorithms, a review. This is the outline of my presentation. I will begin my presentation with the introduction, followed by the fundamental algorithms in Skyline Query. I will start with the block-nested loop, divide and conquer, bitmap, branch and bound and nearest neighbor. The summarization of the techniques employed in each of the algorithm will be presented towards the end of this presentation together with the problem in Skyline Query. Last but not least at the conclusion. The present decade has seen a revival of interest in preference queries that aim at retrieving not necessarily all answers to queries but rather the best, most preferred answers. Skyline queries are a long-studied topic in database and information retrieval communities and popular operation for preference retrieval. It was introduced by a group of researchers that lead by Borsny. In Skyline queries, it returns a set of points that are not dominated, for example, a record X dominates another record Y if X is as good as Y in all attributes and strictly better in at least one attribute. Borsny proposed the syntax for the Skyline operator as shown in the slide, where D1 to Dm denote the dimensions of the skyline. The min, max and diff specify whether the value in that dimension should be minimized, maximized or simply be different. Block-nested loop is the algorithm that works efficient if the skyline is small, and in the best case the skyline fit into the memory. The algorithm usually stops in one or two iterations. BNL algorithm runtime complexity in the best case is ON. N being the number of tuples in the input and runtime in the worst case is ON2. It shows very good I/O behavior, especially if the window can contain the whole skyline. BNL consists of the few steps with two loops, the outer loop and the inner loop. The outer loop visit each object once in the input list. In the inner loop, each visited object will be compared to all identified candidates. If the object is dominated by the candidate from the window, it exits to the inner loop. But if the object dominate candidate from the window, the candidate from the window will be deleted. Eventually, the objects that are remaining in the inner loop are added to the window. If window becomes full, the incomparable objects will be written into temporary file. After outer loop stop, the objects that are completed with comparisons are added to the output list. Divide and conquer is the best theoretical known algorithm for the worst case. It divides the datasets into partitions so each partition fits into the memory. It uses the main memory algorithm to compute the partial skyline of the point in every partition. It works very efficient with the small datasets. In the large datasets, the partitioning process needs the read and write operations of the datasets and this will affect the I/O cost. This is the process of how divide and conquer algorithm works. This a given input list, P1 P5. In the first process, the median of dimension A is calculated to divide the datasets into two partitions S1 and S2. Since points in S2 is dominated by S1, we remove points in S2. Then the median of dimension B is calculated to divide S1 and S2 into S11, S12, S21, S22. In this diagram, S21 is not dominated. We merge the S11 and S21, S11 and S22 and S12 and S22. The final skyline of dimension A and B is P2, P3, and P5. This algorithm introduced by Qian Li Tan. Each object is mapped to a m-bit vector, where m is the sum of the total number of distinct values from each dimension. More specifically, if k is the total number of distinct values on the ith dimension, Then m equals di equals 1 key. Assume that there are key distinct values on the ith dimension and they are ordered ascending. Then, the gth smallest value is represented by key bits, where the leftmost key minus g plus 1 bits are 1 and the remaining bits are 0. This is the example of how bitmap algorithm works. This is the case to determine whether the c-coordinate, 4, 4, is in the skyline point or not. Firstly, each object need be mapped to the m-bit vector where m is the sum of the total number of distinct values from each dimension. Once we have done this encoding process, we need to follow the three other steps of the bit slice process. In step 1, the AND operation is performed to the encoded point of the vertical bit slice 4, 4, 4. The result produced from this operation is 00101000 and it is given as A. In second step, the OR operation is performed to the encoded point of the vertical bit slice 4, 4, 4. The result produced from this operation is 01111111 and it is given as B. In last step, the AND operation is performed to A, produce from step 1, and B, produce from step 2. The result produced from this operation is 00000000. The zero value produced in the bit slice operation shows that there are no other points dominates C, and C is said to be the definite skyline point. Branch and bound skyline algorithm, BBS, is also based on the nearest neighbor search. The important of this algorithm that it is easy to manage the user preferences and it does not require any pre-computation except building the R tree. Also it can be used to any subset of dimensions and it is efficient for both progressive and complete skyline computation. The algorithm uses a priority queue, where our tree entries are prioritized by the mindest value and the mindest of minimum bounding rectangles, MBR, is the L1 distance between its lower left corner and the origin. This is the example how the branch and bound algorithm work. Branch and bound algorithm consists of the few steps. Firstly, select the best R-tree entity to check based on the mindest measure. Next, compute the mindest of the entities and add them into the priority queue. Add the discovered skyline points into the set S. If the top of queue is a data point, check if it is dominated by any point in S or not. If it is dominated, the point is rejected, otherwise it is added into S. Nearest neighbor algorithm is based on the nearest neighbor search and it is an interesting algorithm for the Skyline query which returns the nearest neighbor points to origin as skyline. The great of this algorithm that the first objects are returned very fast and this is a good feature since we do not have to wait until all the results identify to get the first good initial results. This is the example of how nearest neighbor algorithm work. Given a set of input list, this is the distribution of the objects based on age and price. Since object 5 is the nearest point to the root point, 0, 0. Therefore, object 5 becomes the center point for the division of the date space into areas. Again, for each partition, we need to identify the object that close to the minimum bounding rectangle, root. The same process keep repeating until no more data space can be divided. At the end of the process, there are 3 identified skyline point, that is object 1, object 5 and 6. This is the summarization of technique employed in each of the algorithm. In the block nested loop, the technique used is the pairwise comparison that based on the concept of scanning the set of candidate points and placed in memory. In the divide and conquer algorithm, dataset cut into spaces to make it fit into memory. Each of them needs to be processed using the in-memory algorithms. The results obtained from each process are then merged to yield the definite skyline point. In the bitmap algorithm, Every dimension for all tuples is encoded using bitmap, and the Skyline's point is yielded through the computation of fast bitwise. In the branch and bound algorithm, all possible Skyline points are explored via the branch down process in R-tree entries and prune away the entries that dominated by the pre-founded Skyline point. In the nearest neighbor is used to search the Skyline points, and the space is further divided for recursive processing. Skyline Query have caused much attention as it helps user to make intelligent decision over complex data. However, Skyline Query with the high dimensionality facing a problem which known as curse of dimensionality. The chance of one point to dominate another point is very low by increase the number of dimensions. Increasing in the dimensionality will affect on the Skyline results, since the same point of the Skyline can retrieve twice or even more. Most of the fundamental algorithms in Skyline Query works efficiently if the dataset is small. But, if the dataset is large with high dimension, the performance and the accuracy of the retrieving process will be affected. As data tends to grow exponentially due to the increasing of dimensions, a new strategy is required to address these issues. Improving the computation performance without compromising the accuracy of the result of the Skyline Query over complex data is a promising research area and the future direction of this research work. Thank you.